All right, we're going to start section 15.4 in this video, which is Green's theorem. Let R be a planar region with piecewise smooth boundary curve C, oriented counterclockwise. If M and N, have continuous partial derivatives, on R, then now here, this M and N, those are scalar functions, and because R is a planar region, those are going to be functions of just X and Y. So these are each going to be functions of two variables. So then, and I'll write that out in our integral, just so we know. Then the line integral over C of M of xy dx plus N of xy dy equals the double integral over the region R that C is the boundary of. So we have some planar region R and it has some boundary curve C. So this line integral over that boundary curve C is equal to the double integral over the region that C encloses R of the partial of N with respect to X minus the partial of M with respect to Y dA. So what we're doing with Green's theorem is we're relating a line integral over some boundary curve C of some vector field to the double integral over the region that C bounds. So the region that C bounds is R of this particular function. So just to have an idea of what's going on here, we'll draw a little sketch. And I'm gonna write a little note over here to the right of the sketch, so it'll leave some space off to the right. So one thing that we get accustomed to, or we think is the case oftentimes in math, is that it's naturally because we read from left to right, we think that equations only go from left to right because we read that way, but this goes either way. So if I give you a region R, some planar region, it naturally has some boundary curve C. If I give you a closed boundary curve C, it naturally has some enclosed region R. So you can use this theorem either way. So you can evaluate, if you needed to evaluate this integral, but it's easier to do that one, you can do that one. Or if you needed to evaluate this integral, but it's easier to do this one, then you do this one. You do whichever one is the easier of the two. Because we know how to do this, and we certainly know how to do double integrals as well. So now just sketch, whatever, we'll have some curve C, and our curve C is oriented in the counterclockwise direction. So if we were given a curve C, it naturally encloses some region R. So this is C here, and it encloses, so a closed curve C, of course. It encloses some region R. And we've learned in chapter 15 how to do a line integral over C. That's the left-hand side. And we learned in chapter 14 how to do a double integral over some enclosed region R. That's the right-hand side. So what Green's theorem does, or what Green's theorem is doing, or this equality is doing, is relating any line integral, well, any line integral in 2 dimensions, of course, any line integral and that's our left-hand side. So we'll put LHS, left-hand side of the vector field F of XY, which is given by Mn over the closed curve C to a particular double integral and that's our right hand side. So we'll put RHS over the region R for which C is the boundary. Do whichever is easier, or evaluate whichever is easier is probably a better word than do, but do whichever is easier. Left hand side or the right hand side. So if you could be given a double integral that looks like this, but that double integral has to be of the form over some region R where the integrand is of the form n sub x minus m sub y. And that's not usually the case, but it could very well be the case. And if that is the case, then you can instead evaluate the line integral. So we will look at some problems like that where our integrand in a double integral looks like that. So we instead do this one. But in general, a line integral over, if you're doing a line integral of a vector field, of course, they always look like this. So you can always take Green's theorem and evaluate a double integral instead if that double integral is easier to evaluate. All right, so let's talk about a way we can use Green's theorem, or a particular approach where we choose the left-hand side over the right-hand side or vice versa. So in this particular approach, we're going to choose the left-hand side to evaluate a known double integral. So using Green's theorem to find the area of a region R, with boundary curve C given by the vector function R of t equals x of t, comma y of t, where t varies between a and b. So in order to do this, we're going to look at 3 separate integrals. So choose whichever of the below 3 formulas is easiest to evaluate for your curve C. And I'm going to go to the next page and we'll write down the formulas. So in this, now when we see area of some region R, we know how to do that using a double integral. We learned how to do that in chapter 14. So basically, if we're asked to find the area, we're being asked to find something that's of the form of a double integral, which is our right-hand side above in Green's theorem. But instead of doing a double integral, we're going to take that double integral and you do the left and evaluate the left-hand side and do the line integral instead. Excuse me. So first formula we'll look at. So first off, we all know if we do a double integral over some planar region R of 1 dA, we know that that's the area. So if we look at this as, so now we're just going to write 1 in a convenient form for us. So there are a number of different ways we can write the number 1. The most convenient, one of the convenient forms for our particular problem here, and then we're trying to find the area, will be to write 1 as the partial derivative with respect to x of x, which we know that partial derivative is 1, minus the partial derivative with respect to y of 0, and we know that partial derivative is 0 dA. This is 1. If you decided you wanted to write 1 this way for the rest of your life, nobody can argue with you and say that you're doing anything wrong. So we're just rewriting 1 that way instead of writing it this way. So notice here, this is us taking our, remember the first Green's theorem, this is n sub x. So our n is x. And this is m sub y. So our m is 0. So we're just looking at this as, if we say m is 0, and n is x, right? Then this now is from Green's theorem. Green's theorem says that if you do n sub x minus m sub y, that's the exact same as the line integral over c of m dx plus n dy. So that's dx plus n dy, which for us, that's just going to be right there. That's just going to be our m was 0. So this part 0, our n was x. So that's just x dy over c. So, but we know that this left-hand side is area. So then this doesn't, we're not looking at any particular problem. If we were just asked to find the area enclosed by either the area of some region R or the area enclosed by some curve C. Usually we're asked for the area of a region R. If we can find the boundary curve of that region R, then instead of doing this double integral, we can just do this line integral over that boundary curve C. And it doesn't, again, this is not any particular problem. We'll look at some examples of this later. But the reason I'm going over this is because I just want you to see that, yes, we know how to do double integrals, but sometimes it may be easier to do this than it is to do this. So let me give you 2 more formulas and then we'll look at some examples of this a little bit later. So this is one of those formulas. Another one. So let's just put a box around this. So you don't have to go through that process if you are just want to find the area of some planar region R and it's enclosed by the curve C. Your area is always going to be the integral over the boundary curve C of x dy. The next we say the double integral over r of 1 dA. So we're again just going to rewrite the number 1 however is convenient for us. So another convenient way to write the number 1 might be to look at the partial with respect to x of x over 2 minus the partial with respect to y of negative y over 2 dA. And we know the partial with respect to x of x over 2 is 1/2. And we know the partial with respect to y of negative y over 2 is negative 1/2. So we would have 1/2 minus the negative 1/2, or 1/2 plus 1/2, which is 1. So again, this is just a convenient way for us to write 1 in trying to find the area. So here in this scenario, excuse me, our m is whatever we were taking the partial with respect to y. So negative y over 2. And our n is x over 2. So this just is the same as the line integral. So this, according to Green's theorem, this right here is the exact same as the line integral over c of m dx plus n dy, which in this scenario, I'm not going to write out that middle part again. That's just Green's theorem going from there to there. I'm just going to write out this last part. So for this problem, the last part is m dx, so negative y over 2 dx, plus n dy, which is x over 2 dy. This is area. So we can compute area that way, and then we'll look at one more of these. And we'll do an example later so we can see how we pick between, say, this formula and the first one, or this last one that I'm going to write up. So again, the double integral over r of 1 dA. We know that's area. So let's rewrite 1, the number 1, in a convenient form. So here, let's do the number 1 is the partial derivative with respect to x of 0 minus the partial derivative with respect to y of negative y. So we know this is 0. We know the partial derivative of negative y with respect to y is negative 1. So we get 0 minus negative 1, which gives us 1. So we know this is really an area formula, where here our m is negative y and our n is 0. And according to Green's theorem, this right here is the same as the line integral over c of our m, so negative y dx plus our n dy, so 0 dy. So according to Green's theorem, those are the same, but we already knew that this is the same as area. So that's another way we can compute area, is by using that formula right there. All right, so I'm going to stop this video here, and then we'll continue with Green's theorem in the next video by working through some exercises from the textbook.